Good morning, Saturday morning, and this is going to be a video continuing our series on trigonometric functions and trigonometry, where we discuss the trigonometric function tangent. Now, tangent is one of these functions similar to sine and cosine. It was defined back in the day as something involving right triangles, and now we're going to try to extend that definition like we did for sine and cosine so that it works for any angle, not just angles that are in right triangles. Okay, so here are our learning objectives. First one is to define tangent, and then the second one is to use its definition to compute tangents of various angles from the unit circle. And then we'll do some problems related to slope. Okay, so here's our right triangle definition for a tangent. So I want you to recall there's a mnemonic for remembering sine, cosine, and tangent for right triangles, and it's the SOHCAHTOA mnemonic. This was told to me when I was back in taking geometry class, and you probably heard this. But sine stands for, sine is opposite divided by hypotenuse, that's the SO part. Cosine is adjacent over hypotenuse, that's the CA part. And then tangent is the opposite side divided by the adjacent side, that's the TOA. So given the side lengths we have here in my diagram, A and B are opposite and adjacent, and H is the hypotenuse. That tells us that sine of theta is going to be A divided by H, the opposite over the hypotenuse. Cosine is B over H, adjacent over hypotenuse, and tangent would be A over B. Okay, so there's an alternate definition for tangent that comes out of this relation, that tangent is opposite over adjacent. So I want you to notice that if we were to divide sine and cosine, so if we did sine of theta divided by cosine of theta, what we end up getting is opposite over hypotenuse, so that's A over H right here. So this is the sine, A over H, and cosine is B over H. And when we do our division of these two fractions, we take the second fraction and we take the reciprocal of the one we're dividing, and multiply. So A over H times H over B. And what you see from this is that the H's will cancel, and you're left with A over B, which is what tangent is. Tangent is opposite over adjacent. So tangent is just going to be sine divided by cosine. So that's our way of defining tangent. And we've defined sine and cosine for any angle in the unit circle, so we'll just say the tangent of an angle in the unit circle, or of an angle in general, is going to be sine of that angle divided by cosine of that angle. So this now becomes the definition for tangent. Rather than saying tangent is opposite over adjacent, we're going to say tangent is sine divided by cosine. And we'll see that this definition works for any angle around the unit circle. And so something else falls out of this fact. Since sine is the y-coordinate and cosine is the x-coordinate, then that tells us that the tangent is y divided by x, where y and x are the two coordinates for that point on the unit circle. And we already know what this is. Y divided by x for points on the unit circle is the slope of that radius. So now this gives us another frame of thinking about what tangent is and what the tangent means for an angle. If you were to draw that angle on the unit circle, then tangent is the slope of that radius. It's the slope of that line that the angle makes. Okay? So if we think in terms of slope, a lot of things start to make sense. Y tangent becomes undefined in some places, y tangent is 0 in other places, and so forth. So if you think of it as slope, you just quickly get gut checks for your answers, like, oh, does this make sense? Is my slope is bigger than 1 or smaller than 1 or whatnot? Negative, positive, 0, and so forth. Okay? So we've already been computing these problems. We've been finding slopes of radii because we knew the x and y coordinates, so we were just dividing them, you know, y divided by x and finding the slope. So we've been finding tangent this whole time without actually calling it the tangent. Okay, so we'll do a couple examples computing tangent. Let's look at the tangent of 30 degrees. So if I want to compute tangent of 30, I really need to know both sine of 30 and cosine of 30. So I need to understand that unit circle very well to compute tangent. So we know for tangent, or for sine of 30 is 1/2. We were to draw that angle in here. So we draw the 30-degree angle. And we know that the sine is 1/2 and the cosine is √3/2. And at this point, I've practiced enough with the unit circle that I just know these angles, or know these side lengths fairly quickly. Remember that the smaller side is opposite the smaller angle, so for the 30-degree angle, we know the opposite side is 1/2. So that gives us coordinates for this point. √3/2 is the x, 1/2 is the y. So what's the slope of this line? It's the slope of the radius. Well, it's going to be 1/2 divided by √3/2. So the tangent is 1/2 divided by √3/2, which reduces, simplifies down into √3/3. Okay? So this is going to be the preferred way to write 1/√3. You're going to see this thing get rationalized again and again. So we'll just get used to doing it now. 1 times √3 is √3. √3 times √3 is +3. So we get √3 divided by 3 for the tangent of 30. And you can evaluate this with the calculator to just check your work. I'll just go ahead and do that really quickly with a browser. So let me go ahead and go on to type into Google. There we go. Okay, so we'll go ahead and do tangent of 30. And, oh weird, that's -6. Huh, what's going on here? Oh, I noticed that for the calculator, it's got this little rad or degree thing. So if I want to change this, it looks like I'm computing tangent of 30 radians. So if I want to actually, and you can see if, I'll zoom in right here, it says tangent 30 radians. So I want to actually compute this in degrees. So if I want to do degrees, I have to actually type out the word degrees into Google, into the search bar, and that's going to do my answer, or do my calculation in degrees instead. One more reason why I said radians are nicer is that most calculators everywhere use radians to do the computation as opposed to degrees, and it takes an extra step to do it in a degree calculation. So we get 0.577. So let's see if that's the same as √3/2. I'm going to open a new tab and then try computing √3 divided by 3. Excuse me, √3/3, not √3/2. So we see √3/3 is 0.577, and tangent of 30 degrees is 0.577, and they are equal to each other. So fantastic. It's an easy way to check. All right. We'll do another one. Okay. Well, let's compute tangent of pi/2. So again, tangent is going to be the slope, or sine divided by cosine. So if we take a look at the pi/2 radius, so this is in radians now, we're looking at an angle that is pointing straight up. So tangent of pi/2, we're going to recall that sine of pi/2 is 1 and cosine of pi/2 is 0. These are the coordinates 0, 1. And so what's the slope of this line? The slope is undefined. There is no slope because it's a vertical line. And so the tangent is undefined for pi/2. So if we were to try to find the slope of this line, we do sine divided by cosine, we get 1 divided by 0, which is undefined. And Google's going to tell you that. We'll go ahead and test this out in the calculator again. So, okay. So let's go ahead and compute tangent of pi/2. Remember I said that it does its computations in radians unless you specify otherwise. So we'll just do tangent pi/2. And oh, it gives us a very large number. It looks like that's an approximation. So why is this number so big? That's 1.6 times 10 to the 16. Well, when you're very close to that pi/2 angle, when you're really close to vertical, your slope is incredibly steep. You have a very steep line, right? And so it looks like it's doing some approximation here and not giving you the actual correct answer. But tangent of pi over 2 exactly is undefined. There is no answer for that. Okay, so let's carry on. All right, we'll compute tangent of 7 pi over 6. So for tangent of 7 pi over 6, we'll draw that angle, 7 pi over 6. And this is pi, so this would be another sixth. So this is 7 pi over 6. And we draw on those sides to figure out what sine and cosine are. We know that this angle, this side is opposite the pi over 6 angle, so this is going to be my smaller side. This is negative a half. And then this one is negative square root 3 over 2. So the x and y coordinates here are negative square root 3 over 2 and negative 1/2. And so what we'll get if we were to find the slope is we do, again, sine over cosine is the slope. So negative a half divided by negative square root 3 over 2 ends up giving us the same slope as the 30 degree. So if you were to continue this line and do the 30 degree, or the pi over 6, either way you think about it, then you end up having the same slope, and so you get the same tangent. So tangent of 30, or tangent of pi over 6, is equal to tangent of 7 pi over 6. And again, let's verify this with the calculator. So let's go ahead and compute tangent of 7 pi over 6. 7 times pi divided by 6. And that's 0.577. We already know what that is. That's square root of 3 over 3. Okay, the next problem we're going to look at is a little longer. Now we're going to look at a Pythagorean problem involving tangent. So similar to those Pythagorean problems we had in the past. Suppose we have an angle between 0 and pi over 2, and the tangent of that angle is 2. Well, then that's saying what the slope of that radius is 2, okay? So keep that in mind when we're solving this problem. And we've already actually done this problem, but it was phrased differently. We want to evaluate cosine and sine of that angle. All right, starting off, we know that our angle is in quadrant 1 because the angle is told to be between 0 and pi over 2, which is 0 degrees and 90 degrees. So we know cosine and sine are both going to be positive. So I'm going to just kind of remind myself we're here, positive and positive. And so cosine of theta and sine of theta are both going to be positive numbers for this. Just an estimate of what the answer will be, I'm just going to draw it in. So we know tangent is the slope. So I need a line whose slope is 2. So I'm going to draw a slope. This would be slope of 1. So slope of 2 is going to be kind of twice as steep, so it'd be something like that. Okay, so I'll go ahead and erase my slope of 1. So we know that that's roughly where the slope is. So already we have an idea. The sine is going to be more than the cosine. The sine is going to be greater because the y of this triangle is bigger than the x for that triangle because the slope is 2. It's a steeper, it's making a higher rise over a smaller rise. Okay, so with the definition of tangent, we know that tangent is sine divided by cosine, and we know tangent is equal to 2 for this problem, so that says sine over cosine is equal to 2. And so that gives us this relation that sine is 2 times cosine of theta. So I just multiplied both sides of this equation by cosine of theta to eliminate the denominator, and so we end up having sine theta equals 2 cosine theta. Okay, so continuing on, so I'm going to rewrite what we have up there. So we know that tan theta is 2. So that says that sine theta equals 2 cosine theta. And then we also know that we're in quadrant 1. So those are all the things that I remember from the last slide. That's all the relevant information. We're going to apply the Pythagorean identity now. Knowing that cosine squared plus sine squared equals 1, we're going to substitute in the equality we had that sine is twice cosine. So that tells us now, I'm going to do a little color coding here. Because of this equality, wherever I see a sine of theta, I can replace it with 2 cosine theta. So I'm going to put 2 cosine theta in here. And so that gives us cosine squared theta plus 2 cosine theta quantity squared equals 1. So now comes the tricky part, is making sure we use parentheses around this, because when we square it, we get 4 cosine squared theta. So 2 cosine theta times 2 cosine theta is equal to 4 cosine squared theta. So if we rearrange these, we can see we have 2 times 2 times cosine theta times cosine theta. So this is 4 cosine squared theta. Okay? And we add it to cosine squared theta, and that should equal 1. So we have 1 cosine squared plus 4 cosine squared, which yields 5 cosine squared. Dividing both sides by 5, taking the square root, ultimately gives us cosine equals root 5 divided by 5. I'll just do that calculation really quickly. 1/5 equals cosine squared theta. Cosine theta equals square root of 1/5. Multiply the top and bottom by root 5 over root 5, and that yields root 5 over, okay? And again, we know that it's the positive answer, positive, since we're in quadrant 1, okay? Not the negative of the answer, because, okay, and now we know since sine is equal to 2 cosine theta, we found what cosine theta is. We know sine is twice as much, therefore sine of theta is 2 square root 5 over 5. So we found our cosine of the angle, we found our sine of the angle, and at no point in this process did we need to figure out what that angle was exactly to figure this out. We just know, we just used the Pythagorean identity and the fact that tangent was sine over cosine to answer this. And that's the general process for solving these kinds of problems, is to replace tangent with sines and cosines, and then to use the Pythagorean identity, substituting whatever you get in there. Now the same problem, and I would encourage you to do this as an exercise to just refresh, this exact same problem is to find the point in quadrant 2, or quadrant 1, excuse me, on the unit circle. Okay, so this exact same problem is to find the point on the unit circle whose coordinates satisfy t, 2t, and where t is a positive number. So this problem we've already done. Find the point on the unit circle whose coordinates are t, 2t, and where t is positive. Well, we haven't done the t is positive part, but that just tells us that it's in quadrant 1 or quadrant 4. Okay. Well, actually, it has to be quadrant 1 because t and 2t. So we've solved this problem in the past. This is a point who's on the line y equals 2x. It's a point whose slope is 2. Who's on the line whose slope is 2. If you connect it to the origin. So remember, tangent is slope, so if we were to find this point, we'd be finding the exact same values, square root 5 over 5 and 2 square root 5 over 5 for t and 2t. And I'll let you go through solving this. If you want to test that it is in fact equal, you use the unit circle equation and t and 2t as your x and y, and you should get it should just fall out exactly the same. Okay. All right, so with that, I'm going to leave this, finish this lecture, and just talk about what we're going to talk about next time, which will be after our semester final in this case, but may not be in future classes. We're going to talk about reciprocal functions, and reciprocal functions are functions you've heard of, like secant and cosecant and cotangent, or you may or may not have heard of these. They were probably again defined in the context of a right triangle, and we're just going to expand the definitions and look at them for general angles instead. Okay, so that will be next time we'll be talking about reciprocal functions. And with that, I'll see you guys later. Oh, and by the way, got my pie shirt on, and got a little cat. Oh, Mushy is here to say hey. Say hi, Mush. He's very happy right now. Okay, I'll see you guys next time.